In this paper, we present a novel hierarchical reinforcement learning architecture that decouples high-level planning from low-level control. We argue that this helps in solving two major challenges in reinforcement learning: solving long-horizon tasks, and generalization from training to different test environments. We solve these challenges by designing a novel hierarchical reinforcement learning architecture called HYDE. We propose an explicit task decomposition achieved by decoupling the state action space of each layer in the hierarchy. The layers have access to different types of task-relevant information and have separate state spaces. In the planning layer, we propose the integration of an efficient RL-based planner. It receives the global state of the environment, such as the top-down view, and produces subgoals that are more reachable for the control layer. More specifically, it learns a value map of the environment and uses an attention mask to find subgoals in the agent's reachable range. The control layer has access to the agent's internal state and is responsible for the low-level control in order to achieve the subgoal from the layer above. We now present results for three different types of tasks. First, we compare against other baselines in navigation tasks. Then, we demonstrate our method on a robot manipulation task. Lastly, we present a 3D reacher task. For the maze navigation, we train an ant agent in a 3D environment with sparse rewards. The goal of the task for the agent is to navigate the maze and reach the red sphere. For this particular environment, all state-of-the-art approaches as well as our method succeed in solving this task. However, state-of-the-art approaches overfit to the environment and fail when we flip the environment layout without retraining. Contrarily, HYDE generalizes to unseen test environments without retraining. The attention mechanism in the planning module helps the policy output subgoals in the agent's reachable range and avoid obstacles such as corners. In more complex environments with longer horizons and more obstacles, other approaches such as Hiero-LR are often struggling. HYDE, on the other hand, can learn the task, as planning and low-level control are functionally decoupled. We find that in terms of convergence, Hiero is competitive with HYDE in the simple maze. As complexity and environment size increases, the convergence of Hiero slows and the success rate drops. Contrarily, HYDE shows similar success rates and convergence behavior in both experiments. We also find that HYDE can scale to environments with an increase in size of up to 300%. In order to demonstrate that our planning layer is functionally decoupled, we transfer the planning policy across different agents. This is generally desired as training more abstract components of a simple agent is easier. We train HYDE for a simple ball agent and an ant agent. We then combine the planning policy of the ball agent with lower policies of the ant agent. The transferred agent is capable of navigating in complex mazes without requiring any additional training or fine-tuning. Moreover, it even generalizes to unseen environments. We demonstrate that transfer is even possible with a complex humanoid. We again take the planning policy of a simple ball and attach it to a humanoid agent trained to walk towards a relative target. As in the previous experiment, the humanoid can now navigate in unseen environments without any additional training. We now show that HYDE can work on a robot manipulation task. We train a policy with DDPG and HER for object manipulation using a robotic arm. As in the previous experiment, we replace the HYDE control layer of the ball agent with the manipulation policy. If trained in an environment where the goal is to push a cube around obstacles, DDPG and HER can learn the task. Similarly, our transferred policy can solve the task as if it was originally trained for such a purpose. We argue that the policy with DDPG memorizes the path instead of learning to plan. To demonstrate this, we remove the walls from the environment. The policy trained with DDPG executes the memorized trajectory. The transferred policy, on the other hand, does not memorize the environment layout and can effectively plan a more direct trajectory. Moreover, since the transferred policy does not rely on any specific environment layout, it can solve randomly configured environments. Here are two examples of random environment layouts which can be solved with our method. To show that HYDE can use other priors for planning other than top-down view images, We introduce a reacher task, where a robot needs to reach goals in its configuration space. The input to the planning layer consists of a projection of the robot's joint angles onto a map. We can see in this 2D example that Hyde can successfully plan paths for the robot arm. We further extend this to a 3D scenario to show that our planner also works in 3D. Here you can see how Hyde is successfully able to solve a 3D reacher task. Thank you for watching.